लोगोफोर आं मोनसे टपिक्स लानानै फैदों जाय टपिक्सआ भेरि इम्पर्टेन्ट फिजिक्सनि मोनसे टपिक्स 9, 10 आरो कलेज आरो PhD मावग्राफोरनि थाखाय बे टपिकआ जोबोद इम्पर्टेन्ट माखौ लाइट सेल्स होननानै बुङो बा बिदुंनि बोलोजों माबोरैहाय बिरनो हायो रकेटफ्रा बा बेलुनफ्रा बोरै बिरनो हायो व्हाट इज लाइट सेल्स बेनि सोमोन्दै आं फंनैसो बुंनो सानदों। बेनि सिगांनो आंहा गोबांथार एन्सार होनांगौ दंमोन आं एन्सारखौ होजोबनो हायाखै। जेरैहाय मानसिफ्रा सोंदोंमोन बे एफा उन्दैयावनो बोरै प्रफेसर जानो हाखो बा साइन्टिस्टफ्रा भगबानखौ फोथाया बेहा मारै भगबान फोथायो होननाय मोजां कुइसनफोर दंमोन आङो होजोबनो हायासै मोनबा आङो होगोन। व्हाट इज लाइट सेल्स आं बेखौल' बुंनो सानदों। उन्दैयाव बोरै साइन्टिस्ट जानो हायो होमब्ला जोङो मोनसेखौ सिगाङावनो बुजिनानै लानांगोन। स्कुलाव फोरोंगिरिफोरखौ टिचार होननानै बुङो, कलेजाव फोरोंग्राफोरखौ प्रफेसर होननानै बुङो। प्रफेसरा बोरै उन्दैयाव जानो हाखो होनोब्ला नोंथांमोनहा सिगाङावनो मिन्थिखाबाय खोनाखाबाय बियो स्कुलिंखौ 3 इयार्सनिफ्रायनो 5 इयार्सआवनो बे रिकगनिसन मोन्दों बा स्कुलनि जेबो गोनांथि गैया। टेस्टआनो रिकगनिसन होयोब्ला बेथ' टिचार जाहैखाबाय। बेनि उनाव प्रफेसर बा कलेजाव इउनिभारसिटियाव फोरोंनो हानायलाय बेखौ बिसोरनि हादोरा रिकगनिसन होबाय। अब्ला नोंहा स्कुलनि जेबो गोनांथि गैया जों बेखौ बुजिना लानो हायो। नैथियाव जोङो बे रिलिजनखौ बोरै फोथायो साइन्टिस्टआ रिलिजनखौ फोथाया होननानै बुंनायाव नोंथांमोनहा साननो हागौ बियो बुंदों साइन्टिस्टनि खामानिफ्रा माखासे जों फोथायनायनि सायावबो जायो होननानै बुंदों। बियो बथ साइन्स आरो इसोरखौ फोथायो। मानोना जोंनि जायगायावनो बियो फैनानै सिगांनो मिन्थिखाबाय रिलिजना भेरि सेन्सिटिभ इसु होननानै, बेनिखायनो बियो माखासे खोथाफोरखौ बुङाखै। जेरैहाय जोंनि हारिनि मेइन एक्सिस्टेन्सआ जों इसोरखौ भगबानखौसो बुंनो हागौ, जायनिफ्राय जोङो गियान बोलो मोन्दों बेनिफ्रायसो जों गिदिर गोलाव जाबोदों बेखौ बियो सिगांनो मिन्थिखागौ। नाथाय जोंनि बे हादोराव जोंनि बे जायगायाव जोंनि देशआव जोङो अराय सम रिलिजनखौ पलिटिक्सआव लांनो थाङो आरो जोंनि जेरै जोंहाय जौगाबोनो हादों बे जौगानायनि मेइन आथिंखौ जोंनो दानस'नानै होनो सानो रिलिजनजों मिक्स खालामबाय थानो नागिरो जोंनि जायगायाव। बेखौ बियो सिगां मिन्थिखानानै बियो रिलिजननि सायाव बारा बुङाखै। अब्ला गोबाव जाबाय लोगोफोर आङो बे एक्सप्लेनेसन लाइटनि बिबुंनि साननि लाइटनि गोहोजों बा सोरांनि पावारजों माबोरैहाय बिरखंफ्रा बिरनो हायो रकेटफोर बायदि बेनि एक्सप्लेनेसनखौल' सुंद' होनो सानबाय। नोंथाङा मोजां मोनोबा नायनानै लांदो आरो बुजिदो आरो गोजोन्थों। थेंक इउ फर वाचिं.
I'm not sure if all of you looked at the seminar topics, but essentially it's about light sails or solar sails. So these solar sails are basically most rockets nowadays. This is my very crude drawing of a rocket. Use chemical fuel, but the problem is that chemical fuel is heavy, pretty heavy. So if you want to go somewhere, you need lots of fuel, but having lots of fuel will weigh down your rocket, making it more difficult to use that fuel efficiently. But having less fuel means you're not able to go anywhere. So how do we fix this issue? Well, solar sails are a radical new idea, basically stating, so I believe it was the broccoli, I don't know exactly how you pronounce it, that first proposed that these particles, photons, have momentum despite not having any apparent mass. And so now people in the modern day have figured out what if this momentum could be transferred to some sort of lightweight sail to push it around at very fast speeds. And this doesn't require any chemical fuel, just light, which is very conveniently given out by the very bright body in the sky known as the sun. So that means that this could be a viable alternative. There are still questions that people are thinking about for solar sails, such as they still have to be very lightweight to actually travel at relatively high speeds. So if you were to carry a human or any actual equipment on board this solar sail, it likely wouldn't be as effective. So that's one issue that people are thinking of right now. That's probably the biggest issue related to solar sails. But as of right now, people are very ambitious about this project. Some are even saying they could get solar sails to move at somewhat relativistic speed, with one proposal, I believe, proposing for one of these light sails to go at 20% the speed of light, which I frankly don't believe, but it's a very nice proposal. So, what we're basically going to do today is, you can think of a light sail as just a mirror, I guess. So, as a photon bounces into the light sail and gets reflected, that transfer of momentum pushes the light sail around. So, long story short, we're basically going to be focusing on how the angle of incidence and the angle of reflection change if the solar sail is moving, which it obviously has to move in order for it to be effective, and inclined at a certain angle. So there are many people who have done work on this, starting with Einstein himself and continuing up to the modern day. But today I wanted to talk about a pretty recent paper which basically states the relation between, well, let me draw a diagram first of what we'll be talking about. So I don't quite know exactly why I'm drawing this. Let's just draw a velocity right here. And we can say that we have the velocity, you could say, is inclined by theta from the mirror. I guess that's my way of explaining it. Or you could say the mirror is inclined at an angle theta from some plane that we call the ground, and the velocity is parallel to that plane. So then, what we're going to assume is that some photon hits the mirror right at its center of mass, and we're doing this in 2 dimensions, by the way, but I'm pretty sure it can be extended into 3D pretty easily, and it bounces off. Now, of course, the regular law of reflection states that if we just have this incline, and theta I, theta r, then these two angles should be congruent. Now that doesn't exactly hold when we're moving with some velocity v. So, what we're going to assume is measured from the normal. So learn how to draw dotted lines. Measured from the normal, alpha and beta are not the same. But we'll see later that this formula exactly fits into, I guess, Euclidean reflection if the velocity is set to 0. So now we're going to try and find beta as a function of alpha, the velocity, and the incline of the mirror, theta. So this function is what we're overall going to try to find, and it's basically based on just some pretty obvious conservations at the beginning, and a lot of, oh, is this magnetic? Wow. Never seen a magnetic black eraser before. Okay, so this is going to just be based on, of course, the conservation of momentum, the conservation of energy, as well as some relatively tenuous assumptions about the mass. Basically, let's start with what we're at, more detailed diagram, because this doesn't tell us much too. Let's hold this direction parallel to the mirror, the positive y. In this direction, parallel to the normal, the positive x. So now, what I'm going to do is I'm going to decompose the momentum of the photon before and after the collision, as well as the momentum of the mirror before and after the collision, in terms of this reference. So, Here we have the momentum vector in total. Here we have its x component, which is, this is the y component, sorry, oops. And it's traveling in the negative y direction. Meanwhile, this is the x component traveling in the positive x direction. I now think that I should have provided more space. So this is the x, and let's notate this as beta. Okay, so then what we have is the returning ray. It has a negative horizontal momentum. I will try to make this a little more clear in the next diagram, and still a negative vertical momentum. And then meanwhile, when we talk about the momentum of the mirror, then we can also decompose it into a negative y component and a positive x component, with this being 90 minus theta. So let me actually use the different colors that I was provided. It's that one. No, this one's a little too short. And that one. Okay. So a better way to do this would be to color code it, as in making this the incoming ray. Wow. I'm not sure if you can see that, but that's green, and we have the returning ray. So we're going to decompose that into minus py, px, while this is alpha. Then we have the other direction, minus px prime, and then we have, there's got to be a better way to draw this, minus py prime, and then here we have this velocity, which is split up into, I should actually write this is the momentum vector. The x component and the y component, where the y component is negative. Right, so let's actually get on with quantifying these. So the Broy's way of extending momentum to particles was so when p is equal to h over lambda, where lambda is wavelength and h is Planck's constant. So now this is going to be pretty important, and of course from the equation p equals f lambda, we can restate this as hf over c. So now this is going to be the magnitude of the momentum vector for the photon, before and after. So now what I'm going to do is I'm going to split momentum into, for the photon before, into its two appropriate components. So this one is equal to the magnitude of the momentum, which is going to be hf over c, times, well, of course it should be obvious from this diagram that, this diagram that it's cosine alpha. And similarly, this is going to be minus hf over c sine alpha, because it's pointing in the opposite direction. Now, about p prime, which is the momentum vector after, we have p prime x is equal to, and the only thing we can reasonably assume changes other than the angle, which goes from alpha to beta, is the frequency, because everything else is a constant. So we have f prime over c cosine, oh, right, I forgot the minus sign that comes in front, cosine beta, and py prime, which is equal to minus h prime over c, hf prime over c sine beta. Right, so then we have the momentum vector of the mirror, which is just the momentum of the mirror x, which is going to be, well, the momentum of a macroscopic object, relativistically can be described as mv times the gamma factor. So that's what we're going to use here with big M to note in the mass of the mirror. I don't know why they didn't use small m, but this is just the notation that the paper used, so I go with it. And this is going to be 90 minus theta. Cosine of 90 minus theta is pretty obviously sine theta. So P sub x is just going to be this magnitude times sine theta instead of cosine theta, and Py is going to be the opposite. And then the paper assumes, for whatever reason, that after the collision, the mass and velocity and the angle of incline all change. Let me write this a little farther back. Yes. I'll probably use that in a few seconds. So this is going to be m prime, v prime, and the gamma factor changes to account for it, sine theta prime, and py is going to be minus m prime, v prime, gamma prime, cosine theta prime. Right, so now the first three relations that the paper derives for the function that we want are, so the first three relations are: one, the conservation of horizontal momentum, two, the conservation of vertical momentum, and three, the conservation of energy. So, one, when expanded, is going to be px plus capital Px is equal to px prime plus capital Px prime, which, when you plug in, is, oh, I don't know why I added vectors here. Right. So, when you add hf over c cosine alpha, then plus p capital Px, which is mv gamma sine theta, is equal to px prime, which is minus hf prime over c cosine beta plus px prime, which is m prime, v prime, gamma prime, sine theta. Right, so this one is important for exactly one reason that will be revealed later.